Let's start our today's seminar. Today's speaker is Cristina Ana Maria Anghel, and she's going to tell us about UQSL2 quantum invariants for links in three manifolds from Lagrangian intersection in configuration spaces. So very promising title. So let's welcome. Okay.
Yeah, so thank you very much for the invitation. Yeah, it's a great pleasure to give a talk in, well, virtually in Moscow. So yeah, I'll talk about UQSL2 quantum invariants for links and then for three manifolds. And then I will describe a way to see these quantum invariants using Lagrangian intersections in configuration spaces. So my talk will start with a motivation, and then it will be split into three main parts. So the first part concerns the homological tools that we will use. So it's about the algebraic topology which is involved. And then in the second part, we will see a topological model for UQSL invariants for links. And in the third part, we will see a topological model for the Witten-Reshetikhin-Turaev invariants for three manifolds. Okay. So the second part and third part concern different type of objects or links and three manifolds. Okay. If I highlight, can you see? I think you can see. Yeah.
Okay.
Yeah. Okay. So I will start with the motivation. So as the aim is to construct the project for events. And then now by topological model, I mean graded intersection pairing of homology classes in a configuration space of the punctured disk. Okay.
Okay.
And then the idea is this homology classes be given Lagrangian manifolds. And this is because one of this work is to create a new framework for understanding these invariants, and then from this framework to be able to go towards categorifications. Okay, so that is a longer goal, but I just want to say that somehow from what we'll see today, it creates a proper starting point to go towards that direction. And now I will start with a bit of I don't know, a rough description of what happened historical point of view. So quantum invariants initially came from representation theory, and more precisely for links. The idea is that we will fix big N to be a natural number, and we'll call that to be the color of the invariant. And now, if you use the representation theory of the QQS, where Q is a parameter, then it's known that its representation theory, it's indexed by natural numbers. Okay, so for each natural number n, you have an n-dimensional representation Vn. And the construction due to Reshetikhin and Turaev in the early 90s somehow provided a sequence of invariants for links. And these invariants for links are called polynomials. And they are denoted by Jn. So that's one thing that happens if you take the quantum group with generic parameter. Now, a different thing that one can do is to start with a representation theory of the quantum group, where you put Q to be a root of unity. So now you look at Xi SL2, where Xi is the root of unity. And then its representation theory changes completely, and you have a one parameter family of representations. And in a modified way, you can construct an invariant using a Reshetikhin-Turaev type machinery modified due to Akutu-Devuki and Otsuki, and then developed further by Guilhem Paturo. But anyway, the idea is that for each fix the two n's root of unity xi n, you get a invariant called the colored Alexander polynomial. And we'll denote this by phi n. Okay?
Okay.
So the idea is that for each natural number, you have the nth colored Jones polynomial Jn, and then the nth colored Alexander polynomial phi n. And I should say that for n equals 2, the colored Jones polynomial recovers the original Jones polynomial. Okay? So it's a whole family which starts from the Jones polynomial and then has many other invariants. And then the same for colored Alexander polynomials. It starts from the Alexander and then has other invariants afterwards. Okay, so that's at the level of invariant. And then I want to talk about it's on the top side concerning intersections in configuration spaces. So the idea is that the first topological model that was constructed is due to Bigel and Lawrence in early 2000. So they constructed a model for the original Jones polynomial using the homology classes which Bigelow calls forks and noodles. Okay, we will see them later, but I just want to somehow say from the historical point of view how things work. And I should mention other people who worked in the area. So it's Kono, which somehow constructed the identification between quantum and homological representations of braid groups. And also Ito, and then more recently Markel, who provided a more explicit version of the Kono's identification. Okay, and what I want so the first result note, it's a unified topological model for these two families of invariants. So the idea is that you have the sequence of colored Jones, the sequence of colored Alexander, and then what we'll construct is for each n, we'll construct an intersection given by Lagrangians, and that intersection lambda n basically we specialize either to colored Jones or to the nth colored Alexander polynomial. Okay, so at each level we can encapture both invariants in one intersection pairing. So this is what I want to show in the first part of the talk. And in the second part of the talk, I would like to talk about three-manifold invariants. So now, if you want to pass from links towards three manifolds, what Witten-Reshetikhin-Turaev did the group at root of, and then basically representation which have dimensions than the level. So if you fix curly n to be the level of the invariant, if you use the representations v1 up to vn minus 1, and basically construct a linear combination of colored Jones polynomials, you basically can obtain an invariant for three manifold. I'll talk a bit about the definition. What I want to say here is that for each n, we have an invariant for three manifolds, tau n. And that's called the Witten-Reshetikhin-Turaev invariant. And in the second part of the talk, I will show that we have a topological model for this invariant from states of Lagrangian intersections. Okay. And then what I want to conclude of this they a framework from which you can start and then investigate qualification questions. So that's my motivation, or part of the motivation for this work. Okay, so that was a bit of the idea of the results, and what I want to say next, roughly how the model for the Witten-Turaev will look like. So I will not say all the details, but I will just say the main ingredients such that you know what to have in mind. Okay, so it will be a bit rough, but I'll explain the details later. So the construction goes in the following way. So let us fix, as before, curly n to be the level of the quantum invariant. And then we start with a closed-oriented three-manifold M. We as a surgery framed-oriented link L. Okay. Now this framed-oriented link, we can present it as a closure, normal closure of a braid, beta n. Okay. And then, so what we will do is the following construction. So first of all, we will fix a set of indices, I1 up to IN. We can in color or level minus, okay? And we denote by I bar this sequence of indices, okay? And now the idea is that for each such I bar, we will construct two homology classes. And that will be done in the, we will use configuration, the configuration space, these many particles into the punctured disk with 2n plus 3l plus 1 point. So remember, n is the number of strands of the braid, and then l is the number of components of the link. Okay, and then what we will do is to look at a certain covering of this configuration space with step transformations given by z2l plus z. Okay, and we'll use the homology. And in this homology discovering classes. And now these two classes are constructed in the following way. So remember that we have n numbers, I1 up to In. The idea is that we will look at the punctured disk, as we have here in the picture, and then we will cut it in half.
Okay.
We cut it in half, and now inside the n punctured. And then we draw red segments between a base point on the boundary, and then each puncture, and the number of segments is somehow are predicted by the partition. Okay, so we start with I1 segments up to the first point, and then I2, and then so on up to In.
Okay.
So this is the disk. And now in the right-hand side of the disk, we will complete symmetrically. What does it mean? Well, it means that basically, if we look at symmetric punctures, we require that the number of segments which ends into the point k and then the point 2n minus k sum up to the color minus 2. So for example, if you take the first puncture and then the 2nth puncture, you take here n minus 2 minus I1 segments, red segments. Okay.
Well, I think it's too much. I mean, maybe you have a picture for some smaller number. So we have so many configurations.
What is too much?
Well, the number of just, well, okay, just give more detail.
Yeah, so I'll come back to this later. The idea is that if you do this trick, the idea is that for each symmetric pair of punctures, you will get in total n minus 2 segments. Okay. And then, as I said, you will use the configuration space of n times n minus 2 plus l plus 1.
Mm-hmm.
So that is that you take this by the partition, And then you will add some extra purple component in the picture. So there is an extra purple component which goes towards the middle. I'm highlighting it now. It's a bit of a delay, so I think you can see it now. Yeah.
Okay.
And then we have L extra circles, which I highlight now. Start from boundary and then go around punctures. Okay, and then if you take your time and then think how many curves we have drawn, I will tell you that we have drawn exactly this many curves. This number, n times n minus 2 plus L plus 1.
Okay.
I mean, that's not the essential point, but the idea is that that partition somehow prescribes this subset of curves. This is what I want to say. And then what you do is to basically take the product of these curves and then look it into the unordered configuration space. So the product of these segments will give you a submanifold in the ordered configuration space of half dimension. And then what you can do is to quotient it to look in the unordered configuration space. So that will give you an homology class. And then what you can do is to try to, you will leave this homology class towards that particular covering. So that's the way of constructing the first class F. Okay. And then the second homology class, see more details later, but just to have in mind. So the idea is that you have a configuration space, a covering, and then you construct everything in the basis, and then you lift. And so the second homology class will be given by product of configuration spaces on this kind of circles, which are drawn around symmetric. Okay, you can see in the picture n plus 1 circles. And then you take the product of configuration spaces on these circles. And this product will give you first an homology a submanifold in the configuration space, which will be later lifted to the covering. And that will provide you a second class L. Okay, it's a lot to take in one go. I just want to say where we are going. This will be the last part of the talk. And now with these two homology classes, the idea is that we will use a Poincare-Lefschetz duality, which is in the homology of the covering. Okay, so basically you could intersect these homology classes and then obtain a polynomial. And moreover, this homology group will carry a braid group action.
Excuse me, and how do you prove that these are Jones or Alexander? Do you use Kane relations or what sort of proof do you
No, I mean, no, I use, so I start from the fact that Color Jones and Color Alexander come from the representation theory. So from the Reshetikhin-Turaev construction.
Okay.
And then I construct this kind of classes homologically. And then I prove that the result given by this intersection is the result given by the Reshetikhin-Turaev construction. Okay. And so it's Color Jones and Color Alexander, or Witten-Reshetikhin-Turaev.
And you wrote the product over XCK, and then I don't understand what you wrote.
Yeah, I mean, I didn't talk about it yet. So the idea is that for the moment we have these two homogeneous, and so we will construct. So remember that we fix this I, which is the sequence of indices. Okay. Now we construct an intersection pairing, which we call Lagrangian intersection, lambda I, which depends on the braid beta, which is given by the following formula. So here you have some factors, which I think for the purpose of this moment, I'll not insist very much on them. So they're just some variables.
So I don't understand
and
the
then
exponent. Excuse me, I don't understand the exponent. So x ck to what?
Yeah, so the idea is that C of k is a color, it will be a coloring. So you will color the 2n, you will color the L variables, x1 up to xl.
Yes.
Somehow following the closure of the braid. So you
Yes.
take the braid and
what
then.
What is in the exponent? What is in the exponent?
And
so
in the exponent is a framing of the link. So the link is framed.
Oh, okay, it's framing. Fine.
It's the framing, and then you basically you look at the framing which corresponds to each special function. Okay. Okay. So these are two products which come from framing corrections. This is the place that they come from. And then the main point is that we start with the first homology class Fi. We act with a braid where we add trivial strands on the right. And then we make the pairing with. And now this pairing will give us a polynomial in these variables. Okay. So it will be a polynomial in Z of x1 up to xl, y1 up to ywell, and b. And then what we do next is to complex of coefficients. So by adding from this ring to C. And this morphism, I will show the formulas, but that's called psi with these indices. Yeah. So what you should have in mind is you have two homology classes. You act with a braid on the first one, you make the pairing with the second one. And basically this pairing will give you a polynomial in some variables, and then you will specialize it. This is what you should have in mind. And I will go through all the details later. Okay. And so the main result where I would like to arrive is topological state sum model for this WRT invariant. Which tells us the following things. So if we of the invariant, and then we present a fold as a surgery around a framed link, and then we present that link as a closure of a braid. Then the Witten-Reshetikhin-Turaev fold is obtained as a following state sum. So here is the usual normalization, which appear in the WRT invariant. And then we have a state sum over all indices I bar as before. And then the idea is that for each I bar, you look at this lambda I bar of beta, which is the Lagrangian. And what you do is many specifications of it. So you take the sum over all colorings n1 up to nl, which can vary between 1 and the color minus 1, such that in some sense the coloring is bigger than the index. I will say that this later.
So what's in the numerator? So is it 1 to the minus 1 or 1q to the minus 1, or what is it? So sometimes I don't understand.
The quantum number 1. Hello?
Okay, yeah.
So it's the quantum number 1, which means psi minus 1 inverse.
Okay.
Yeah.
Okay.
And then there is the sum of this Lagrangian intersection lambda I, specialized over all colorings, which in some sense sit on top of I. And I will explain what on top of I means. Okay?
Mm-hmm.
Okay, so this is where we'll arrive. And now I start slowly with homological tools. So I'll talk about homological representations and how to construct coverings and use the homology of the coverings. So what we'll do is to fix 3 natural numbers. So that we fix mk 3 natural numbers, and we will use the nth puncture dn, and then look at the configuration space of m points in this puncture disk. And I want to say that it's an unordered configuration space. Okay, and now further on, we'll define a local system. So the idea is that we will fix an additional very 0 and n, and this k will.
Excuse me. I just wonder whether we can make some more punctures to get some more homology classes. So you see, what we are doing now, we are trying to upgrade invariants when we have some additional homology and homotopy. Is it right that if I add some more punctures, then I will have more freedom in getting some homology classes and hence getting invariants of for example, the same thing in maybe some manifold with something cut away, maybe. So, I want to upgrade whatever possible by using some homology, additional homology and homotopy information. Can I make more punctures here?
Of course, I mean, and it's anything. I mean, here, and it's a natural number. You can make as many punctures as you want.
Okay. Well, and now my question is whether we can use additional punctures to make some more homological information on intersections. So if we have intersections, then somehow starting from somewhere, we can say, okay, this intersection with respect to that one has some homotopy information.
So about the homotopy information, I do not know. It's definitely an interesting question, but I don't know.
Well, it would be nice because actually we are always stuck into the invariants we already have. I mean, all invariants are polynomials for knots, and for manifolds even less. We have some polynomials at roots of unity. And the invariants we are interested in, they are something like pictures or elements of free groups or elements of some homotopy classes. So if we can upgrade, well, you have numbers, you have something, but if you can upgrade it by some covering or by some punctures, then we will be able to upgrade the known invariants to something new.
Yeah, okay, yeah. So anyway, here for this part of the talk, I will use some particular configuration space and so on, but this construction is general. Okay. So all what I wanted to say here is that for this construction, we start with the pi1 of the configuration space, and then we first make the evaluation, which means that we go towards Zn plus Z. And now why we go towards Zn plus Z? So the idea is that we have, since we start with the punctured disk, we have in the homology, we have n generators, which are given by these sigma i's, where basically you start that you have a base at the boundary of the configuration space, call it D, which in the punctured disk means that you have m points, okay? And then what you do is to start from D1 and then go slowly around the ith puncture, and then keep all the other components fixed. Okay. So that will give you a loop in the configuration space, CNM, which we call sigma I. Okay, and then, so in this fashion, we get n generators. And then secondly, what you can do is to get you can get an extra generator, which is given by the fact that you start with the base point, D1 up to dm. And then you swap components of the configuration space. And then keep all the other fixed. Okay, so it's exactly the blue curve in the picture. Okay.
Mm-hmm.
Right. So now you have n+1 generators, and then you take the abelianization, but in a certain way, such that you use this extra parameter k. So basically, you send sigma I into X for the first n minus k punctures, and you send the other ones into minus X. You will count monodromy around the first punctures and then around the last punctures with different orientations. And K tells you where to stop and then change the orientation. Okay, and then you send the generator delta into this D. Okay, so overall you have a local system which goes towards Z plus Z. And you denote it by phi minus K, because it depends on this K. Okay. So what you take out of here, you have a morphism from the pi1 of the configuration space towards Z plus Z. And then what we will do is to consider the covering which corresponds to this configuration space. Okay.
Okay.
Right. So now we do some extra things. So we fix W a point on the boundary. And we also fix a lift of the base point D to the cover and noted by DT. And the idea is that I just want to show you which are the main tools that we will use. They look a bit fancy, but actually what we will do is to use some very precise classes given by precise Lagrangians. So the homology classes might look a bit fancy, but everything is very explicit. So there are three main tools. So they're done by the homology covering space. And we'll take three main points. So the first point is a certain subspace in the Borel-Moore homology of this covering space. And we denote it by H and M and then K. Okay. And then this homology group will carry a braid group action because the braid group is a mapping graph to this. Okay. Secondly, you will use homology group with respect to the boundary. And we denote it by H and M minus K and delta. Okay. And the main point is that you have an intersection pairing between this homology group. And that's drawn with Martin Palmer. It's, I mean, to such that the classes we talk about really makes it's a bit fiddly, but it can be done. And all what I wanted to take away from this is that if we have an intersection pairing, which goes between this homology and the dual one, and sends you towards Z of X plus minus 1, D plus minus 1. Okay? And what you should have in mind is the Poincare-Lefschetz type duality. Okay? And this intersection pairing, as I wrote here, it seems like it's defined at the level of the covering, but actually it can be computed from the base configuration space using some paths to the boundaries. Okay, so it's basically encoded in the configuration space CNM. Okay, so this is now the first setup, and now how we will construct the homology classes. So the idea is that our classes will look to reducing them it will be similar. The difference between the number of segments or the number of functions or some. The idea is that we will use partitions. We denote A and M, the set of partitions of M into M natural numbers. So for each such partition, E1 up to En, what we can do is to associate a submanifold in the base configuration space, Fe. And the procedure of constructing this is very similar to what you saw in the beginning, but this is somehow at the lower level, it's easier. So you start from the boundary, and then you draw E1 segments to the first puncture, E2 to the second puncture, and so on, En up to the last puncture. In total, you have drawn M segments, which means that if you take the product in the order of the confusion space and you quotient it, you obtain a well-defined Lagrangian in the unordered confusion space CNM. Okay, so the idea is that this class, this manifold F, is given by the product of curves. Okay, and the curves are these red curves which I have drawn in the picture. And secondly, we need a second piece of data, which will be very important for computations, namely a path in the configuration space. And in this particular example, I choose the path in the following way. So basically, I start from each red segment, and then I go down towards the boundary. And there are these pink segments. And then I denote their union seen as a path in the configuration. So eta will be a path in the configuration space from D, from the base point, towards our manifold Fe. Okay, and now what you do is the following thing. So you take this path, and first you lift it towards and so you D tilde. Then you lift the path towards eta tilde. Now you look where this path ends, and then you lift your submanifold F at the end of that path. Okay, and that will give you a Lagrangian in the covering, and then given by that Lagrangian. That will be Fe. Okay, so what you should take out of here is that you have a geometric support which is given by a collection of curves, these red curves in the punctured disk, and then you have a path to the base point. And now out of these two piece of data, you construct an homology class. Okay, so from now on, when I say homology classes, basically I will draw collection of curves in the punctured disk. Procedure of constructing the homology exactly by this recipe. Okay. Right. So these are basically the geometrical tools that we will use. And now I will start with the second part, which concerns the topological models for link invariants. Okay, so I will talk a bit about links, and then at the end I'll talk about the submanifolds. And then basically links will first model, and then we have an embedded model. We will see both, and then at the end we can go to the other. And it looks like they actually both might be very, very, very useful for geometrical purposes. Okay, so for this part, we start with N, the color of the invariant. And then L be an oriented link, and as before, we presented the closure of a braid beta L. Okay. So now I'll talk about the model with embedded Lagrangians. So the idea is that, as before, for each index I bar, components are less one. I will construct a particular homology class, and which I will denote by U tilde. And this construction is proceeded as follows. So you take the punctured disk with, so remember, this is the number of punctures. And this is the number of particles. Okay, number of particles. Okay, so in this case, we will use the 2n-1 punctured disk, which I have drawn in the picture. And then we will use the configuration space of these many particles, n-1 times n-1.
These are something like forks and noodles, right?
Yeah, but they're generalizations of forks and noodles.
Okay.
In the language of Jules Martel, I think he has something which he calls code sequences, which are very similar to these ones, but use configuration spaces on segments, and then these are somehow variations of that. They look similar, but they're not precisely the same thing. And now the idea is that, as I said, you start with a punctured disk, and then you cut it in the middle. So that you have n points on the left and then n-1. Okay, and then you use partition in order to draw segments towards the punctures 1 up to n-1. So you draw I1 segments towards the puncture labeled by 1, I2, and so on up to in-1. And then you complete symmetrically such that in total, the number of segments which end into symmetric punctures add to the color of the variant -1, so this n-1 here. Okay.
Okay.
So now if you count in total, you have drawn n-1 times n-1 segments, or well, curves, these red curves. And what you can do is to take your machinery and then which give you Lagrangian in the base configuration space. And in order to obtain a homology class, you need a second piece of information, namely a path to the boundary. And for this particular model, the path to the boundary, it's this pink path eta, okay, which is quite curvy, if you see. Okay, so starts from the boundary and then go symmetrically towards symmetric, the symmetric punctures. Okay, so the idea is that with this piece of data, geometric support, and then path to the boundary, you can produce an homology class. And that will be called UI tilde. And that will be the first building block. And now the second building block will be constructed using figure eights. So these figure eights are exactly the noodles. But now what we do is to take configuration spaces of n-1 points on each figure eight. Okay, so you draw the noodles, and now you take ordered configuration spaces of n-1 points on each figure eight. Take their product and then look it into the unordered confusion space. That will give you an immersed Lagrangian, which has dimension exactly n-1 times n-1. Okay, because you have n-1 points and you have little n-. Okay, so this will give you a Lagrangian in the base confusion space. And then secondly, what you do is to take this particular path from the boundary to this figure 8. And we denote it by eta. And we will use this path and then this geometric support in order to produce a homology class, which we call G. Okay. What take out for each index I, we have a class UI and then a class GN. So this basically doesn't depend on I. And so these are the building blocks. And now the homology classes that we will use are given by the following formulas. So the second homology class, it will be this G, which is fixed and will not modify it. I try to highlight it, but I don't know if you see it. Can you see it now? It's this G. And so the first homology class E, which we denote ENN, it's basically a linear combination of all these UIs over all possible indices I, such that the components vary between 0, 0, and the polar -1. Okay. So basically, with construction, we constructed for each n, for each big N, we constructed two homology classes, EN, N, and then GNN. Okay. And now further on, I want to make a notation because we'll use it, namely a specialization of coefficients. So the idea is that if you take C, an integer, we will denote by psi with these parameters a morphism from the ring with three variables towards the ring with one variable, which sends you u into this q to the lambda, x into this, and then d into this. Okay. And now that if I do not write the first part, so if I write psi with just two indices, it means that we go from the Laurent polynomial ring just into variables. So we skip this u part. Okay. So if we have three indices, then we go from three variables towards one variable. If we have two indices, we go from two variables towards one variable. Okay. And now, so the idea of logical model via these immersed functions. Namely, what we can do is the following. So we start with our link. We present it as a closure of a braid. Okay. And then now remember that we have two classes, this ENN and then this GNN. Okay. And we consider the following intersection. So IN of beta, it's constructed from the first class E, on which we act with a braid where we add n-1 trivial strands. And then we make the pairing with G. So that will give you a polynomial in, okay? And then the idea is that this IN recovers the n-squared Jones and the n-squared Alexander polynomials. So more specifically, if you want to obtain the n-squared Jones, Jn, you start from this Lagrangian intersection In, you specialize it using this specialization, and then you get the and you add the Fleming correction. And dually, if you want the nth colored Alexander, you start from the same intersection, you correct it. Okay, so in some sense, this intersection contains information which captures both Colour Jones and Colour Alexander.
What about Humphrey?
So that's a very good question. I'm thinking about this. It seems like something should be interesting about it. I don't know to say something very precisely. For n equals 2, you get something which captures both Jones and Alexander. Okay.
Well, that's really cool.
Yeah, but the question is, so this In, it's not on the nose the link invariant, or at least the method of proof is that you show that in each particular case give you Colour Jones or Colour Alexander. But in order to go towards Humphrey and something like this, you really need to check homologically what happens. And, I mean, I'm thinking about it now and I'm working about this, but I cannot say a very precise answer. But certainly the question about the invariance of this In, it's interesting. And that's one of my further directions.
Great, thank you. Okay, let's go further.
So that's the first result. Now, you asked about noodles and forks. I just want to make a comment about noodles and forks and Bigelow's model. So, what is the relation to Bigelow's model for the Jones polynomial? So, if you take this theorem 1, 2, the classes that I showed you give you exactly the geometric supports which are used for forks and noodles in Bigelow's picture. Okay, but overall the model will be a bit different because somehow here we use normal closure of braids, whereas Bigelow has flat closures. So the overall model is a bit different. But the homology classes have the same geometric supports. And I just want to sketch a proof why you get these forks and noodles. So just as a reminder, for the indices I1 up to n-1, which vary between 0 and the color -1, we had two main classes, this U and this G. Okay. So, and remember that this U was constructed by looking at symmetric punctures and saying that in total you should have the number of segments which ends into symmetric punctures, which add up to n-1, big n-1. And now let's see what happens for big N equals 2. So big N equals 2, it means that we look about Jones polynomial. And so -1 is 1. These are either 0 or 1. Yeah. And which means that the homology class E2, it's basically a linear combination over all I of this UI tilde. And then now let's think about this UI tilde. So the idea is that we should start from the boundary. Then we should towards the first, and that's I1. Okay. And now the idea is that this I1 is either 0 or 1, which means that symmetrically for the last puncture, we should draw either 0 or 1 segment, which is A1. Looking at symmetric punctures, you either have a segment which ends into the left, or you have a segment which goes to the right, but not both in the same time. Okay, and now for the class G, so for the dual class, remember that for G and N, you take configuration spaces of big N minus 1 points on this figure 8. And now for the particular case where N equals 2, it means that you take configuration spaces of 1 point, which means that you take exactly the figure 8s, which are the figure 8s which appear in Bigelow's picture. Okay, so that's G. And now I want to say a remark about this class, the first class, E. So what you can do is to which is on the tree, slowly push it to the middle. Okay. And now when you push it to the middle, the idea is that you have a base point, and then you draw segments to the left and to the right with the condition that you take either a point to the left or either a point to the right. And then basically you can see that you can construct your model using basically just smoothenings of these classes, which are given by these symmetric segments around symmetric punctures. So basically, if you look at the point N and the point N, you take something to the right, it tells you that you have in your geometric support a continuous segment which goes from N-1 to N, and so on and so forth. And yeah, so here I want to say that basically this is similar to the forks which are used in Bigelow's picture, and then this one is given by the noodle. Okay. Right. So that's the first corollary. Now, the second corollary that I would like to mention is that using this model, you can show that ADO invariants come from Z plus Z2n covering spaces. Namely, that the n-squared Alexander invariant, which is a non-semisimple quantum invariant, comes in Z plus Z2n covering of a configuration space in the punctured list. Okay. So in other words, you can see the variable of the Alexander polynomial as the variable of this Z from the deck transformation.
So have you ever tried any non-commutative coefficients? So that's what I aim at. So if we try to do not homology, but rather homotopy.
So I mean, not in this work, not in what I'm talking about now.
So you have another work? It would be great.
I mean, I'm working on either many projects, but what the aim for this part is to understand Jones and Alexander using topology, and then go further and somehow start from that framework to see more topology, basically.
Okay.
Okay. So the main question that I would say about here is that so this is it's a powerful model, and you see basically the geometry from where the 8s which appear in Bigelow's picture come from the quantum point of view. But next I want to show that we can have a model with embedded Lagrangians, and then we can have simple lifts to the covering. And then the fact that we have this kind of simple lifts, we will make the model suitable for computations. Okay. So the model is embedded. So now I'll talk about the second model. So, and answer this question that I said here is that ideas, and the ideas are the following. So in order to get embedded Lagrangians rather than immersed, what we'll do is to replace the symmetric, the 8, which appeared in the second class, with circles. But now if you want to replace an 8 with a circle and still get the well-defined homology class in the covering, then you have to change the local system. And this is where this extra parameter k comes into. So the idea is that we change the local system, and then if you change the local system, then we can use circles instead of figure eights. And we'll also add an extra puncture just to encode some coefficients which appear in the previous model. Okay, so don't now are constructed in the following way. So as before, we have an indexing set I, where the components vary between 0 and then -1. And the idea is that we start with the punctured disk. And as before, number of segments which the instruments add to n-1, as you can see here. But what we do is to add an extra puncture in the middle. And segments which go from the boundary towards the puncture. So anyway, with this procedure, you get this number of segments. And now you will take the path to the boundary given by these straight lines towards the boundary, straight vertical lines. So you see, it's very easy. I want to remind you that in the previous model, the very curved. I'm waiting to scroll down.
Okay, so let's proceed.
So what I want to say is that in this previous model, the paths to the boundary were curvy, which somehow makes it a bit more difficult from the computational point of view. In the second model, as you can see, the paths to the boundary are straight, and that will be somehow very, very natural and useful for the computations. And so basically this geometric support plus this set of paths give you an homology class Fi. And dually, you will take configuration spaces on circles around symmetric functions rather than figure eights as before. Okay, and this time the paths are given again by straight lines, which will be useful for the next part. Okay, so the idea is that in this way you get two classes. For each I you get Fi and then Li. And the second theorem tells us the following thing. So this will be a unified model through embedded Lagrangians. Okay. Namely, let us consider the following polynomial in 3 variables. So lambda n of beta, which is given by, so now we add an extra parameter u and use it for the framing correct part. Now we take the state sum over all i's of the intersection, so the beta which act on Fi, and then we make the pairing with Li over all i's. Okay, and that's a polynomial in 3 variables. And then the idea is that this polynomial in 3 variables captures precisely the n-squared Jones and n-squared Alexander. So the n-squared Jones is from this state sum specialized using this specialization. And the n-squared Alexander is obtained from this state sum. So the same state sum, same polynomial in 3 variables, specialized in a different manner. Okay, so what I want to say is that the corollary of these two theorems is the following. So you see, we have and of the invariant, we have squared Jones and then n squared Alexander. And then in the first theorem, or out of the first theorem, we can have an immersed state sum, which is a polynomial in 3 variables. And this polynomial captures both Jones and Alexander with different specializations. That's the first result. And what we saw just now is that we have also an embedded state sum, this lambda, which captures both, so lambda n captures jn and then phi n through different specializations. Okay. Basically, to models contains both invariants in a geometrical picture. And I just want to end with a corollary. So for n equals 2, it means that we see the original Jones polynomial and Alexander polynomial from the same geometrical and topological picture. And I will show you an example of computations. So for let us take the trefoil. And then this is a closure of sigma to the power 3. Yeah. And now the idea is that remember that I1, we have, in this case, n equals 2, which means that n minus 1 is equals 1. So we have just one index, I1, which can vary between 0 and the color minus 1. But now the color minus 1 is exactly 1, because we are at the n equals 2 case. Okay. So basically in that formula, we have just 2 situations. Either I1 is 1 or I1 is 0. And then if you think about the punctured disk, if I1 is 1, then you have to draw the class F, which looks like, and then if I want, you draw the class like this. Okay. And now if you, the idea is that you have to act with the sigma in this part, the mapping class compaction, which will modify you the red curve, which will wind around the puncture. It will not modify and I have drawn on the same picture because you can read everything on the same picture. And basically all what you have to look is to look at the intersection points between these geometric supports and then compute the intersection pairing. But now I said that the intersection pairing, even if it's defined on the configuration space at the covering, it is encoded by the geometric supports and then the path to the boundaries. Which means that basically we can compute the intersection pairing just using this intersection points and come using this path to the boundary. Okay. So in the end, if you compute this, if you just add up corresponding to the formula, you get lambda 2, which looks like this, and it's a polynomial in 3 variables. And this polynomial recovers, so if you do the specialization for Jones, then you get the Jones polynomial of the trefoil. And then if you do the specialization for Alexander, you get the Alexander polynomial of the trefoil. Okay, so this was an example of computations with the embedded model. But what I want to say is that you can proceed and use the other model. This immersed model will give you again an intersection pair which contains both Jones and Alexander, but geometrically in an immersed way. Okay, and so this is all what I want to say for this part. But so the idea is that from now on we have Coro Jones and Coro Alexander from the same intersection of Lagrangians, and then the idea is to study geometrically what happens with these homology classes. and what is the topology which is underneath this model. One of the aims is to go towards categorifications. And for Jones and Alexander, meaning for Hega Florent for one homology. Okay. And now in the last part, I just want to make precise the objects that I briefly talked about in the beginning. Namely, what happens for the WRT, for the three-manifold invariant. So for three-manifold invariants, you start with a closed oriented three-manifold. And just to remind a bit the context, you fix the level and then 2n root of unity. And then the WRT invariant, it was a complex number, tau n. Okay. And so now the definition as it comes from the representation theory due to Reshetikhin-Turaev tells us it is constructed in the following way. So you look at the three-manifold as a surgery along a link, a framed oriented link. And now what to do is to use the so-called Kirby color, which this Kirby color is basically a formal linear combination of representations of UCSL2. Basically, you will use the n representation for all n less than curly n. Okay, so you use all representations bounded by the color. And then the Kirby color omega is given by the linear combination of Vn's weighted by the quantum dimensions of Vn. And this quantum dimension number n in brackets, and I wrote here the formula. Okay. And the idea is that the Witten-Reshetikhin-Turaev invariant tau of m is so here is a correction, and then the main point is to take the polynomial where you color each strand with the representation omega. In other words, you take a linear combination of all color Jones polynomials, somehow weighted by these quantum dimensions. Okay. Okay, and then I just wanted to say, which is this will be a quite complicated local system. But the main idea is that we'll have 4 main parameters. So we have n and m as before. K will play the same role. It will count the opposite monomers. But then we have something extra, which is this L bar. So the basic idea is that we take n punctures and we add some extra punctures. And those extra punctures will contain some extra variables, which we will use. Okay? So this is this blue part. Now, M will be the point in the preparation. And this K will be, as before, we'll count up which points go with positive monodromy and which points go with negative monodromy. Okay, and now, so the idea is that we will look at the puncture disk with n plus 3 L bar punctures. Okay, so what you should think about is that as before, as we had the setup before, we have n main punctures. And now you add 3L extra punctures. Okay, and then these 3 extra punctures are useful because somehow if you go around them, you get extra variables. So in some sense, in this model, you have something which is which contains more variables. But I'm not, I mean, in this part, I'm not saying about homotopy, invariance, or these kind of things related to your question. Yeah, but these punctures are related to the just the mono, to have some extra monodromies around them.
Yeah, but can you incorporate this monodromy into the invariant? So can you upgrade your invariant by adding monodromy?
I don't understand the question.
I mean, try to add some more punctures and try to use some monodromy around these punctures to add them as coefficients to the invariant.
I mean, this is what I did. I mean, these extra punctures are used in order to have extra variables. So the correspondence is that extra punctures means extra monodromies geometrically, but in the polynomial means we have extra variables. That's a dictionary.
Okay. Okay.
Okay. So now the idea is that you look at this configuration space. So you have n points on the line, and then you add 3L extra punctures, which you draw 3 by 3 vertically, as I have drawn here. Okay. And then the main point is that by adding these extra punctures, you get extra one. So you have these kind of loops which go around the principal punctures, and you have n of them. Gamma and gamma bar, which go about around these blue punctures. And then you get an extra part, which is eta. Okay, so and the delta is the usual generator, which just swaps to puncture. Okay, so you get this rich local system, and rich local system builds 3 type of generators. So X, Y, and D. And I have drawn in the right hand side here how you count the monodromies. So here you see the first n minus k punctures are counted with x squared. So sigma goes to 2x into this language. And then the last ones will be counted with opposite monodromy. Okay. And then for the blue ones, you have extra variables. This was the idea of adding these extra points. Okay. And these extra variables are useful for the WRT invariant actually. Okay, and then so now you have this local system, which is the composition of and you will use the covering of the configuration space corresponding to this local system. Okay, and so what I want to point out is that the homology of this covering it's a module over 3 types of variables. You have the x's, which somehow encode the main monodromies around punctures. You have the y's, which encode the monodromies around the blue punctures. And you have the d, which is the swapping in the configuration space. Okay. And this is the technical part, which I don't want to insist a lot, but yeah, for the purpose of being rigorous, I should say very briefly. So we will work as with links and braid closures. So the idea is that we want to act with a braid group. And basically, in order to act with a braid group, we will use we will look at the link as a closure for braid. And if the braid has n strands, it means that we will have a coloring of the n strands given by the components of the link. So I have a coloring from n strands towards L colors, C. And to this coloring, we can associate a specialization of coefficients, FC, which doesn't do much. It's basically what you can imagine geometrically by taking a braid closure. So you send the variables which corresponds to the punctures to the same variable, but the index given by the component of the link. Okay. So you have a morphism from these variables x, y, and d to the variables x, y, and d again. Okay, and the main point is that we will use the generalization of the homology that we presented before, homology of the covering, an homology of the covering with respect to the boundary. And the main point that I want to say is that we have an intersection pairing. Pairing between this homology H and L M K tensor is dual in this rich ring. Okay, so it's Z of XL Y1 YL and then D. Okay, and yeah, I think a bit rushed, but I'm running out of time. I just want to say how you construct the regressive homology classes that I showed in the beginning. Okay, so that's about the classes. So context is curly N is a level, M it's surgery around L, and then L it's beta close. And in order we will work in the configuration space of these many particles. In the punctured list. And then the idea is that if you look at the link in the of a braid, basically this picture will give you a coloring of 2n+1 points with n colors given by this formula. Okay, so you basically color the 2n strands following the links of the components of the link, and then you add an extra color, which you an extra puncture, and you declare that has color 1. You get a coloring with L colors, and it's a coloring of 2n+1 points. Okay, and then so what we will use is the following. So n, so the number of punctures will be 2n. So n is the number of states. We use 2n+1. L is the number of components of the link, and that will be the extra blue punctures which we add. The weight will be exactly this. Number of strands times the level minus 2+1. And the last points will be counted with opposite mononomials. Okay. And in this framework, we will use this homology group, H, N, L, M, K. And I just want to point out how you count the monodromies. So basically you have here the main punctures. And then on the main punctures, you count the monodromies with x's. So variables are x's. And the indices by the, okay? And I wrote that orientation. So left hand side it's anti-clockwise, and right hand side it's clockwise. And then for the extra blue punctures, you count the monodromies using the variable y. Okay, in this fashion. And so the idea is that you have the configuration space of this many particles in this punctured list. And instead we of the covering, which is a module over Z in 2l+1 variables. Laurent polynomials in 2l+1 variables. Okay, and now I just want to show more concretely which is the first homology class and which is the second homology class. Okay, so as I said in the beginning, x's will be indexed by indices I bar, whose components vary between 0 and the level -2. And the construction is similar to what we saw before, but it's a bit more delicate in the sense that we take the punctured disk, we put the 2n+1 main punctures on this line, and then we add 3L extra punctures. Okay. And now what you do is, and we take care to put the extra punctures such that if you think about the closure of the braid, then this part, okay, this is 1 bar PL bar, okay? And then the geometric support that we use is similar to before. You take I1 up to the first picture up to IN. Then you complete symmetrically up to the color -2. And the new part here, and which is very important for the model, is that you add L extra circles, which are these circles which I draw in yellow. So basically, you draw circles which create a monodromy around the middle puncture, the middle puncture. Okay, and basically these extra circles will have the property of encoding curvature. So by drawing geometrically these circles and then adding these extra punctures, you encode exactly the Kirby color. And the second homology class will be given by configuration products of configuration spaces on symmetric circles around punctures, where here one should be careful exactly how to put the punctures around the circle. Okay, and I wrote here the number of points which you have in the configuration. So you have configuration spaces of n-1, n-2 points almost everywhere, except those L special places where you have the blue punctures, where you add one more particle. Okay. So out of this, you have FIN, the first family of families. And what you can do is construct a Lagrangian intersection. Okay, so you define lambda I of beta to be the product of the variable x's using the coloring, and this F is the framing of the component which corresponds to those special punctures. Again, this is given the x's using the coloring, and now you take the intersection between, you take the braid, and in the right hand side of the disk you just act with a trivial braid which has n+3l+1 components. So act on the class F and then make the pairing with L. So the idea is that when you do this, you will obtain a polynomial in L because the pairing was defined such that it takes values n+1 variable to l+1. And now we'll use the specialization of coefficients psi to go to complex numbers, which is defined in this way. Okay. And so now I just want to conclude this saying the statement again, now that we have the objects defined. So the theorem tells us that if you fix a level, then the Witten-Reshetikhin-Turaev invariant of M is this framing correction which appears in the original definition. And then the state where the multi-index I is between 0 and the color -2. And now you remember that for each I, you have a Lagrangian intersection, lambda I. Okay. So basically what you have to do is to take this lambda I and some specific, you add the specializations for the colorings N1 up to NL, which are free to go between 1 and the level -1. But with the property that each component ik, it's less than n with the k -1. Okay, so in some sense you take I and then you add up all specializations which corresponds to colors which are bigger than I, which sit on top of I. Okay, and since it's quite late, I will just finish it. I just want to say a conclusion of this result. So basically, geometrically, what we see from this theorem is the following. Tau n, it's encoded by this state sum which is by this lambda I, and then count all the specializations of it. Okay. So in other words, it means that for each I, we can draw the picture, which is this picture. We have the class, the red class F, and then we have the class F. Here in the pink part, we'll act with a braid and see what happens with that the red class when we act with a braid. And then we have to intersect with the class L. Okay, so for each I, you take Fi, act with a braid, and then intersect with Li. In other words, following this formula, we see that the with invariant of M, it's encoded by the intersection points between these two Lagrangians. Okay, for all I. Okay, and this is an intersection in a fixed configuration space. Okay, and yeah, I'll end here, and I just want to say that somehow from this Lagrangian intersections, this is a proper framework to start and see what happens if you try to see the Lagrangian for homology, which come from this from this pair of Lagrangian intersections for each I, because all these Lagrangian intersections are in the same manifold. So in this picture, you do not see anymore the Witten-Reshetikhin-Turaev as a linear combination of Colorado polynomials. Everything is fixed in one particular manifold. Okay, and I think I'll end here.
Okay, so thank you very much for a beautiful talk. Dear friends, let's thank the speaker. And are there any questions or comments? Unmute your microphones or write on the chat line, please. Any questions, comments? Well, okay, it's great that we have invariants which deal with intersections, because they are usually object for further upgrading and further categorification. So is the most recent paper best to start with? This is a question from Heather Dye. So which is the paper best to start with? You are not audible.
Yeah, so they are constructed one after the other, basically. So I think the easiest to read are the one with a embedded model, and then from that one somehow that is used for as a starting point for this WRT one. So it's the embedded one, which is the second one, and then the last one. Yes. The first one, which is basically that's the most important one, and somehow it builds up all the theory needed for this. It's more technical and longer.
Okay, more questions? I think we can share everything, or share all papers, share all references. Well, and have you given a talk about that at the seminar by Lou Kaufman and Roger Fan?
No.
They have a very nice seminar. I think they can appreciate it. Lou Kaufman.
I mean, I'd give a talk, yeah.
Yeah, okay. And it would be nice to discuss it in more detail, well, more privately. So we discuss our science on the weekend or maybe some other time. So it would be nice to discuss it. So thank you very much. It was really a beautiful talk. So
thank you very much for the invitation. Yeah, thank you.
Thank you.
Okay.
Thank you.
Bye.
Bye.